Alright, this next bit is going to be widely applicable. You're going to use this for geometry and also for rounds 3 and 5. This is all about triangles. Now I mentioned before that if we know two angles and one side of a triangle, we can figure out all the rest. And figuring out all the rest is what this next bit is going to be about, specifically for right triangles. Consider this situation. You have a right triangle, and you know one more angle. What else do you immediately know about this triangle? Well, you know the third angle. And if you think about it, you know the shape. You know that all triangles with right angles and 32-degree angles are all exactly the same shape. They may not be the same size, but they're all the same shape. And that means that the different sides are relatively to each other the same for any triangle with those angles. Let's say I drew another one that was smaller, but also had a 32-degree angle and a 90-degree angle. If this is like 55% of that, then this will also be 55% of that. And there are certain relationships that are always true in these situations. Now I can create a triangle with a 32-degree angle and a right angle, and I can figure out exactly what what the ratio between any two sides are. And those different ratios have different names. A name for this ratio, a name for this ratio, and a name for this ratio. And we'll get to those in a bit. But to start with, just this idea. If we know a right triangle and one other angle, we can know the ratios. Now, a lot of the time these ratios are some crazy decimal. But for a couple of specific instances, the ratios are something very memorizable, and it's expected that you'll memorize them. First of all, the triangle with a 45-degree angle. And secondly, the right triangle with the 30-degree angle. So consider what we know about a 45-degree right triangle. Right triangle, 45, the other one, if you subtract the others from 180, you find that this is also 45 degrees, because the triangle has to add up to 180 degrees. And once you know that this is an isosceles triangle because of the base angles theorem. You know, if these two angles are the same and these two sides are the same, whatever length this is, this length will be the same. Now, how long will this be? Well, let's talk about applications, okay? Let's say you have a 45, 90-degree angle, and you know this side is 7 inches long. Now you know this side is 7 inches long. Great. So smart we are, right? But how long is this compared to those two sides? Well, if we don't know this side, we can still use Pythagoras. X squared plus the same thing squared equals 2x squared equals, let's call this y for now, the third side squared. The third side squared. Square root each side, and you get the following. Y equals x times the square root of 2. So that's the length of this third side, x times the square root of 2. So this it's expected that you'll know. When you have a right triangle with a 45-degree angle, the other angle obviously is also 45 degrees. These two sides are the same length, and the hypotenuse is square root of 2 times bigger than either of the small sides. Here's an application. Find the length of these two sides. Okay, well, if this is root 2 times larger than this, then we would divide this by root 2 and find that this is 10 root 5. And this would also be 10 root 5. Done. This is, I believe you'll find this in the MCAS formula sheet also. It's just one of those things that you're given and you're supposed to know and use, but they give it to you in a formula sheet also. Right. Also, the 30, 60, 90 triangle. If this is 30, this is 60. The reason they bother with this one is because one of the ratios is actually really clean. Whatever the shortest side is, the side opposite the 30-degree angle, the hypotenuse is always exactly double that. And again, if you use Pythagoras, 2x squared equals x squared plus y squared, you can derive, you can figure out that y, the length of this, is whatever x is times the square root of 3. And this is also something you'd be expected to be able to use to get around a 30, 60, 90 triangle. For example, let's say you have a 30, 60, 90 triangle where this is 30 degrees and this is 90 degrees. They've told you this. Or maybe they've told you that this is 60 degrees instead. Once you know this, you know that, okay, let's say they told you that this is 20 inches long. Well, this is the longest side. The shortest side is always half of the hypotenuse, right? If the hypotenuse is 2x and the short side is x, that means this has to be half of that, it'll be 10. And this will be root 3 times whatever the short side is, 10 root 3. So this is something you guys can be expected to use. It has uses in, let me give you an actual useful use, okay? Let's say you had a equilateral triangle, 60 degrees, 60 degrees, 60 degrees, and we know that each length has a length of 10 inches, thingies, whatevers, cubits, to go biblical. And you wanted to know, how tall is this triangle? Well, if you look at this, that splits this into a 30-degree angle and a 30-degree angle. This is a 90-degree angle because it's straight up. And then, this is the hypotenuse. This is the shortest side opposite the 30-degree angle, so that makes this 5. Well, of course that's 5. This is also 5. But then that makes this 5 times root 3, which is about, I want to say 8.5 or so. Yeah, so that is an actual use. You can figure out how tall a triangle is if it's an equilateral triangle. You would have to go, take one of the side lengths, divide it by 2, and then multiply it by root 3. That's how tall. Actually, that thing, root 3 over 2, you're going to see that in a little bit. Okay? Now, let's talk about the ratios in triangles in general. Because even though these are the best known, these aren't the only ratios that you might run into. There are there are relationships between triangles that have been given names. Let's take any generic triangle. It's got an angle, and this is a right angle. Now, if I knew just one more angle, I would know the shape of the triangle. And if I knew that one more angle, I'd be able to tell you, by comparing it to other triangles that have been made in the past with those angles, exactly what the ratio between any two sides are. If this was a 30-degree angle, I could tell you the ratio of this to this would be half. This is half of that. If this was 45 degrees, I could tell you the ratio of this to this would be 1, because this would be the same as this. 1 of x over x is 1. And the different relationships became given names. If this is the angle from which you're looking, then the sine of that angle, this is how it's written in mathematical notation, the parentheses are optional, is the, basically what they did is they came up with a long table of values. Somebody took a 1-degree angle, a 2-degree angle, a 3-degree angle, and measured the ratios for all of those triangles. And then they found a mathematical way to calculate it. And then they created a shortcut for your calculators called sine. And what it does is it finds you the ratio between specific two sides. It'll always compare the side opposite the angle to the hypotenuse. So let's say I found out that this was a 20-degree angle, and I asked the calculator, hey, I know that this side is 15 inches long, but I want to figure out how long this angle is. I could type into a calculator sine 25, and it would tell me, oh, the ratio between the side opposite and the hypotenuse is 0.413. And then I'd say, oh, so this is 41.3% of that. Well, if 0.41, if the sine of 25 is 0.413, and I know the hypotenuse is 15, then I will be able to multiply each side by 15, and 15 times 0.43, why, that's about 6. So now I know that the length of this side is about 6, maybe 7. Good for me, I'm so smart. Using sine, I know those ratios. But that isn't the only ratio that matters. What if I want to find this side? So people started memorizing how to label a triangle. From any angle you may look at, there's the side opposite that angle you're looking from. There's the hypotenuse, which is recognizable because it's opposite the right angle. And then we need a name for the side next to that angle. And in English, we would say, in modern English, we would say the side next to the angle that isn't the hypotenuse. In older English, the word used was adjacent, meaning next to. And so the ratio, then they needed a name for the different ratios. The ratio between this and this was called cosine. Let me write these out. If you wanted to spell them in English, it would be S-I-N-E is sine. Cosine, C-O-S-I-N-E, and the shortcut in your calculator for that, it will be cos, C-O-S. So if you're like, well, my triangle has a 25-degree angle, and you type in cosine 25, that'll tell you the relationship in any triangle between the side adjacent to that angle that isn't the hypotenuse and the actual hypotenuse. And the third relationship is tangent, the third common one. Shortcut is tan. Alright, so those are the three relationships, and I can tell you several values that sine has. In a triangle with a 60-degree angle, what is the situation? Well, from a 60-degree angle, the sine is the relationship between the opposite side and the hypotenuse. The opposite side from this angle is this, and the hypotenuse is that. So the ratio would be x root 3 over 2x. Cancel out the x's, and you end up with root 3 over 2. So in any triangle with a 60-degree angle, the side opposite the 60-degree angle divided by the hypotenuse of the triangle will always be the same as the square root of 3 over 2. Because all right triangles with 60-degree angles are the same shape. Their third angle is 30 degrees, and they are all the same. They may be different sizes, but the ratios between the sides are always the same. There's a whole bunch of these that are based off of this that you're expected at some point to memorize. Usually this happens during pre-calculus, but if you're here in math theme, it's something that you're going to want for round 5. Alright, I'm ready to continue. Let me just hop over here and wave around. Alright, so numbers you should be able to memorize, and all of these actually just come from these two special triangles. Yeah, there's 15 things you have to memorize. Actually, there's even more, but let's handle this sensibly and you'll see that there's actually not that much to memorize. Let's go over sines. Let's stick with the angles that are sensible to see in triangles, because it's very rare you'll see a 0-degree angle in a triangle, or a right triangle that also has a second 90-degree angle, right? So let's start with the middle ones. Sine of 30 degrees. In a triangle with a 30-degree angle, the ratio between the opposite and hypotenuse will be the ratio between the opposite and the hypotenuse, x divided by 2x. X divided by 2x is 1/2 because you reduce it by x. In a 45-degree triangle, the ratio is of the side opposite to the 45-degree angle compared to the hypotenuse is x over x root 2. That cancels, and you could write 1 over root 2, but then if you've taken algebra 2, you probably know how to rationalize this to make sure the denominator stays rational. This becomes root 4, which is 2, and in the numerator you have root 2. So the sine of a 45-degree triangle is written as root 2 over 2. Let's find the sine of a 60-degree triangle. Well, this is also a 60-degree triangle because the 60-degree angle is over here. Sine would be the side opposite the 60-degree angle compared to the hypotenuse. X root 3 over 2x, the x's cancel out, you have root 3 over 2. Now, do you see the pattern here? 1 over 2, root 2 over 2, root 3 over 2. This should be root 4 over 2. And it will be. Of course, you can simplify that. Root 4 over 2 is 2 over 2, which is the number 1. But we'll explain that more in detail later. This is actually root 1 over 2. It's just root 1 is also 1. And if you back it up, that'll be root 0 over 2. Root 0 is 0. So 0 over 2 is just plain 0. Now, I'll explain those two results in a little bit more detail. Actually, let's do that now. Let's imagine for ourselves a right triangle that has another right triangle. Well, that's not really possible, right? I mean, actually, we'd have to zoom in. This side would have to be exactly 0 in height. And then, it could actually, it's not really much of a triangle, but it could theoretically exist. Theoretically, there's a right angle here, and immediately that right angle happens again and it goes back. This is if I've zoomed in infinitely on it, and this is 0 degrees. This is 90 degrees, 90 degrees. Woohoo, weird triangle. Of course, the height of this is 0, and this is just the same line twice. I've only drawn it apart so you can have an idea what they imagine it must be like. So what's the sine of a 0-degree angle? Well, the side opposite the 0-degree angle is length 0, divided by the hypotenuse, which is 1. So 0 over 1 is 0. And how about the sine of a 90-degree angle? Where here's a 90-degree angle. What side is opposite this 90-degree angle? 1. And the hypotenuse is also 1. So 1 over 1 would be 1, and that's why sine comes out as 1. The sine of 90 comes out as 1, sine of 0 comes out as 0. Similar situation for cosine, sort of, because cosine is a different relationship. And so, even though we use the same triangles, it'll give us different numbers. So how about the cosine of a 30-degree angle triangle? Well, if you have a 30-degree angle triangle, the side adjacent to it is x root 3. The hypotenuse is 2x. So what is root 3x over 2x? Cancel out the x's, you have root 3 over 2. Cosine of a 30-degree angle is root 3 over 2. which looks familiar because it's the sine of this. Why does that make sense? Because if you're dealing with a 30-60 triangle, what is opposite the 30-degree angle will be adjacent to the 60-degree angle. So what is opposite to 30 will be adjacent to 60, and that's why they have the same answer. And the same thing will happen here. And since 45-degree angles, adjacent and opposite are both the same length, x, it's only the hypotenuse that's different. In that situation, this is going to be the same. And you'll see that it follows exactly the opposite pattern. At this end, you'll have 1. At this end, you'll have 0. Tangent's a little odder. It shows up less frequently in everything. But because, take a look at this. Tangent is opposite over adjacent. You know what else is opposite over adjacent? Sine over cosine. Sine over cosine means opposite over hypotenuse divided by adjacent over hypotenuse. Those hypotenuses can cancel out and you end up with opposite over adjacent, which is tangent. So if you want to find the tangent